Alright, this is the last installment to the forces unit. So we talked about Newton's first law, second law, third law. We talked about mass, gravity, tension, normal force, spring force, elastic force. We talked about friction, and now we're going to talk about something kind of related, but that kind of stands on its own. So the universal gravitation is definitely going to be part of forces. It is a force, but it's not one that we use when we're solving an FNet type problem. It's kind of its own little world, this universal gravitation. So, something we know about gravity. If we know we have a 1 kilogram mass on the surface of the Earth, we can figure out that it has a force of gravity of 9.8 newtons because Fg is mg. We know this. We've talked about this at multiple times. And this is the force caused by the Earth. But let's just stop there and think about Newton's third law that says that there's equal and opposite forces in every situation. So if the mass is feeling something from the Earth, then the Earth actually, it must feel a force too that is equal and opposite based on Newton's third law. So how can we reason this? And the same type of thing. So that's if we're on the surface of the Earth. If we go bigger and we talk about gravity between Earth and the moon orbits Earth because there's gravity. And we have things on the Earth like tides that are affected by the moon and its gravity. So how can we calculate these kind of things? How can we calculate it when all we know that Fg is mg, but that only works for being on the surface of the Earth because g varies, it changes. And that's something that we need to fix. So if we're going away from the Earth, the things that gravity would depend on, if we're at the surface of the Earth, if it depends on mass, then if we're going away from the Earth, that hopefully shouldn't change. So, and it doesn't. So it actually will depend this time on both masses because we have to have two objects. And if we have more mass, just as we do on the surface of the Earth, we get more Fg, which is what we expect. The other thing is if we're at the surface of the Earth and g is, and we know that we've got a certain amount of gravity, if we go and hike up to the top of Mount Everest, we expect to be less. And that's because we're farther away from the center of the Earth. So the distance matters as well. So the distance between objects' centers. So it's not just the surface of the objects, but the object's centers matter, such that we have more distance, so we get farther away, just as we did going up to the top of Mount Everest. We get farther away, we get less Fg. So our relationship there is inverse instead of directly. And Newton came along and said, well, I know these things. I'm going to make a relationship so that Fg actually depends on m1 m2 over r squared. Now this isn't an equation yet because there's some constant value that Newton could not figure out. It took a little bit while for another guy to come around and measure that, and we'll see that in a bit. But we want to look at just this part. So Fg depends on the two masses and the square of the distance between them. So this helps us with planets. This helps us with things going around in circles for planets again. And we want to know how Fg depends on masses and the distance between them. So let's pretend we doubled one mass and see what would happen. So we would get an equation that would be 2 m1 m2 over r squared. Now if we look at just this portion, this is our original. And so looking at that, we can conclude that we have, if we double one mass, we will double Fg as well. So let's take the same approach now, but instead of doubling one mass, we're going to leave the masses alone and we're going to double our distance. So we're going to have m1 all over 2r squared. Now, before we can see, we actually have to simplify that exponent on the bottom. And so we get 4r squared. Now let's highlight what part our original is, which is just that part, which allows us to see that we have 1/4 of our mg. So we've actually cut it in 4 by doubling our distance. So the distance makes a bigger factor than the masses. It changes it more than changing the mass. So the farther you go away, you get faster, less force the farther you get away. Now, if both masses are doubled and the distance is halved, what does that do to Fg? Well, I'm going to leave that one, and we're going to see the solution to that in class. So, like I said, Newton couldn't figure out what the constant was, and it took this guy named Henry Cavendish about 100 years later to do an experiment, the Cavendish experiment. We can search that up. To measure G, to measure this constant, and he called it big G. And so we get a full equation of Fg equals big G times mass 1, mass 2, all divided by r squared, where we have the mass of each object, the distance between the center of the masses, and our constant value G, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. It's a very, very small constant, and that affects how much gravity we have depending on our mass, because if the constant's very, very small, we have to have something that's very, very, very large to go against that very, very small number to make it somewhat big. So let's do some calculations. If we're going to calculate the force Fg of 1 kilogram mass on the surface of the Earth, we already said it should come out to 9.8 newtons, but we're going to do it with this formula this time instead of using mg. So we have to have the mass of the Earth, 5.98 times 10 to the 24 kilograms. You have to know the radius of the Earth, because that would be the distance between our object and the center of the Earth, because we want the center of our two objects. And we have our other mass. So now we just have to set up our equations. We have big G, m, e, other mass, and the radius of the Earth squared. Plugging everything in, 6.67 times 10 to the negative 11 Newton meters squared. And so it's just plugging and playing at this point just to get our answer. And when you do that, as long as you don't forget to square it, which some of you will do at some point, you will get 9.80 newtons. So it does give us the same result, which is important. And that's good. So that tells us that our universal gravitation applies to everything. And mg is just a specific situation when we're on the surface of the Earth. You can use Fg equals mg for any of the problems that we solve. You'll know when you're doing a problem to use Fg as the universal gravitation. It will be very, very obvious. Like this next question where you're asked to calculate the force of gravitational attraction between a girl and a boy standing 2 meters apart. This is just asking for Fg between these two. So you go with the same equation. I'm not going to rewrite the equation this time. We're just going to plug in our numbers. We have same constant. There's always lots to write out with this formula, just because it's a pretty large constant to write out. And we've got two masses. We got 52 kilograms and 79 kilograms. And we've got 2.0 meters squared. So, Valentine's Day is coming up. If this applies to you, the force of gravity between you would only be a very immeasurable and insignificant 6.9 times 10 to the minus 8 newtons, which is a very, very small number. If you think about centimeters, would be times 10 to the minus 2. Millimeters is times 10 to the minus 3. Micrometers times 10 to the minus 6. And a nanometer, so this is almost like a nanonewton, would be times 10 to the minus 9. So we're very, very, very small. You would never be able to feel this no matter how close you got to somebody. So let's talk about the force of gravity between something that would be able to feel it, which an example would be the Earth and the Sun. So we need to know the mass of the Earth, we need to know the mass of the Sun, and the distance between them, r. This kind of information will be on your equation sheet. If you need it, it will be there. You won't have to memorize those types of numbers. Though, some of them you'll just know because you write them down so many times. So in this case, again, plugging everything in, 6.67 times 10, negative 11 newtons, meters squared, kilograms squared, times 5.98 times 10 to the 24 kilograms, times the mass of the Sun, 1.99 times 10 to the 30 kilograms, which is on the order of 6 magnitudes more than the Earth. So that's a lot more mass. All divided by the distance between them, 1.5 times 10 to the 11 meters squared, which this will calculate out to. If we think about those exponents, we've got times 10 to the negative 11, just do some exponent work, 10 to the negative 11 times 10 to the 24 times 10 to the 30 divided by 10 to the 11 squared. Well, there is a lot of big numbers there, a lot of big numbers. And in this case, we're going to get a big number result. So we get 3.53 times 10 to the 22 newtons. Now that is a lot of force. But that's why the Earth stays in orbit around the Sun. That's the force that it feels from the Sun as it's going around in its orbit. So this equation, you'll see it in questions like this where you're talking about two masses and the gravitational attraction between them. Most of the time you'll be calculating Fg. You might be doing other things, but most of the time it's something like that. So you've got 5 problems there to check out. If you're curious, and I really think it's interesting to read about gravitational fields and Einstein's theory of gravity, which is quite different than Newton's theory of gravity. So you can read those, 182, 183, 184, 185. Read that stuff. And we'll see you in class. And as always, physics is awesome.